right, welcome everyone to another life science session here at the Wolfram Institute. Today, I'm super happy to report that, recently two papers came out from the work that Xerxes and I had been doing for some time, even before joining the Institute, but obviously continuing in the last few months at the Institute as well. So we wanted to have the opportunity to tell the world that this research is out there. It's one of the, in my opinion, more exciting meta-mathematics developments that really pave the ground for discovery, and there's a real chance for mathematical kind of development and actual new mathematics to be described. So so in this live stream, I wanted to go over, point you to the relevant papers that recently appeared, give you some brief explanation of the main gist of the content of those papers, and then show you some of the future directions that I am thinking about currently, and hopefully we have some time to actually brainstorm and discuss a bit of the sort of maths and science of that. So with that being said, let me share my screen to show you these papers. Let me put your faces somewhere I can see them. All right. So this paper was our first introduction to this whole concept of higher-arity science. We use this term higher-arity science in a very broad sense. So I welcome you to search for this. This is very easy to search. This is now in Advances for Complex Systems. And we go over a bunch of examples of potential sort of systems. And let me just give you a hint of kind of, actually, where's the index? So the index should be up here. Oh, there was an index in the beginning. All right. So basically, I have an index here.
So Carlos, I think this is the third paper. The second one was Advances in Complex Systems. That one has an index, not this.
So, but this is the one in Advances, right?
No, this is the one in Complex Systems, and the other one is Advances in Complex Systems.
Oh, you mean the, right.
Yeah.
Beyond binary.
That's right.
Yes, absolutely. So, so this is the preprint.
Yeah, but the published version had a slightly different title because we updated several things. That's right.
So anyway, I didn't want to spend too much time on those anyway. So so these are the titles. So I believe we're so ill prepared for this second paper. Apologies. What's the quickest way to? What did we say this was the? Aha, that's the one. Here we go. So, so this is another of the papers. You have this set of papers. So here, I think this is the PDF. Is this just the journal page? Yes. So you can get the spectrum. This introductory paper in complex systems. You have this more technical one that addresses how the more technical implementation of the mathematics we propose in different fields will proceed. And then finally, the one that I wanted to mention today, which is about the pure mathematics of this area of research. So no applications in mind, just the actual formal theory that came out very recently, and that's kind of what I wanted to tell you about today. So this one has basically the the main contribution is our definition of what we call a Plex diagram. And initially, we focused the paper more on the small discovery we made that a certain algebraic structure known as a semi-heap could be characterized with a rewrite system in a similar way that you can characterize binary associative algebras with rewrite systems. But one of the reviewers very kindly suggested that the diagrammatic language that we developed to make this discovery was important enough, and it was good enough that we should make the paper about that diagrammatic framework. And so that's why we renamed it, basically. So if you find the preprint heaps of fish, we give it a much more mimetic name. I mean, you get pictures of fish, but actually the first link is our paper. So that's kind of funny enough. So the content is essentially the same. So you can head over to heaps of fish, our preprint, and you will get essentially the same content. Now, this version has some substantial edits in the body of text, but it's essentially the same content. But it does have this focus on the formalism itself. So what's the formalism? So let me just show you the main explanation of the formalism. So it is effectively a way to deal with arrays, right? So many people call arrays tensors. So these would be things that you have index numbers, so to speak, index scalars. You have a collection of scalars with a set of indices that identify them. And this formalism is essentially a way to graphically represent these things in a way that is relatively easy to manipulate, at least better to manipulate than if you're dealing with 4 or 5 index objects and you have many of them and you have to push them around and so on. So the basic idea is the following. So these indices, as I say, just indicate different sequences of elements in a semi-ring. So you just have something like the natural numbers or the real numbers, or semi-ring is quite general. You just basically need an additive structure and a multiplicative structure that distribute with respect to each other. And so Plex diagrams essentially are graphic representations of indexed arrays of these elements, right? So, for example, here what we call a one Plex is just basically a point or a node. This would represent a vector in usual parlance, right? That you have V is a one index object. Similarly, here M will be a matrix with indices I, J. Here A would be what we call a cubic matrix with indices I, J, K, and so on, right? So we, for example, take basic operations to be just edgewise, right? So your nodes are the indices and your edges are the objects, the arrays themselves. And so, for example, component-wise addition or component-wise multiplication will just notationally denote it by that, just inscribing the symbols. But most importantly, we can describe the phenomenon of what's generally called incidence, just for the graphical representation. So what incidence means is that some indices might be the same in sort of computer science terminology, or might be belonging to the same space more mathematically. If you're thinking of these indices as being basis expansions on vector spaces, this would be the same vector space and so on. So when we have for example, this collection of arrays, say a matrix IJ and the sort of cubic tensor JLK, the fact that the index J and J from these two objects run over the same values and we want to identify, we express by giving it the same name. And so therefore, if you are to express this in the sort of minimally, so graphically minimal form, you would end up with something like a hypergraph, right? Where you would scatter all your distinct vertex names or distinct index names as vertices, and then you will distribute your edges as your arrays. So by default, we take the convention that when you write such a diagram, you are implying a product that looks like this, right? So like as it is common in algebra, the juxtaposition of objects means multiplication. So that is no different here, juxtaposition of graphic elements here means multiplication, but it means multiplication in a very specific way, which is by being incident on certain indices. So here, the object that you see on the left here has I, J, K, L indices, and that's what the specific values of this whole thing, which is a 4-index object, is given by this formula. So you take the I, jth value of M, you multiply it with the jth, L, kth value of A, right? That's simple enough. So in a way, this is like doing a Hadamard product that is index-wise, right? So of course, this generalized.
I have a question. So is that like a contraction?
No.
Oh.
So this is a contraction is very similar, but we explicitly don't contract, right? So this is like a Hadamard product. So matrix multiplication is a contraction. Hadamard product is just component-wise multiplication, right? So this incidence product represented here is a Hadamard product. Is Hadamard-like, right? I mean that would be what a Hadamard product is.
But you are assuming Einstein summation convention, right? The J is sum up or not yet?
Not here. Okay,
Wait,
later.
So is that dot product, the conventional dot product per?
No. So this is just
Okay.
the product of the semi-ring. So these are numbers, M, I, J, A, J, L, K. These are numbers. These are just components of an array.
Mm-hmm.
And I am just exploiting the semi-ring structure. I'm only assuming that my indices run over some semi-ring. Call it V here for values. That could be an integer, rational, real, complex, whatever. And this is just a convention to express this particular kind of product. So we will see in a second how we recover contractions, and because that's where we're going. One note here is that if for simplicity in this paper we represented the edges as being undirected, just not to load visually all these diagrams. So that means that technically, if you want to extract an index formula from these hypergraphs, you have an ambiguity of sequencing your indices. But if your hypergraph actually contains the internal ordering of the indices, then there's no ambiguity, and the hypergraph and the specification of the product are exactly equivalent. So of course you can do a lot of things. Yeah.
Sorry. But if you just specify ordering on each hyperedge, it's not gonna specify ordering of all the indices across multiple edges, right? So
Correct.
it's still ambiguous.
Correct. So yes. So there's two ambiguities. You're right. So there's an ambiguity of internal symmetry of indices, and then there's an ambiguity of the global ordering of all edges of all indices, right? Yeah. So this is of course solved by what we call a sequentialization, which is just an arbitrary choice for. I mean, you always have a finite number of vertices, so you just arbitrarily sequence all of them, and then that is the canonical order in which they're going to appear in the final expression. But it is a big redundancy. So you have a lot of potential variations of this differently looking algebraic formulas that correspond to the same hypergraph as a isomorphism class of hypergraphs, right? But anyway, the point here is that this is a shorthand notation at this point. We are not making it into a formal system yet. Later on, we will take it more rigorously as a formal system, but this is mostly a shorthand notation. So these are some examples of expressions that you would, many physics students, I'm sure, are familiar with dealing with these kinds of products. I mean, here we use the dots to really make explicit that there is a multiplication going on, but often we just drop the dots because these are just multiplications of scalars. So this, look like the typical expressions you would find when you're doing your general relativity homework or something, like, lots of indices and lots of letters with letter sub-indices and so on. And what's neat about this is that when you look at this kind of thing, it is difficult to kind of pick out the patterns of indices in this mess of letters, right? Like if you read this, it's kind of hard to first identify, wait, L is actually repeated in all of them. Like it takes a little bit to process. It's like visually a bit noisy. However, if you look at the diagram, it's clear. M and U have one common index, and they have three indices each of them. And so that's kind of the selling point here, right? Like you're able to at a glance grasp the index structure of an expression just like that. All right, so here we land into what contractions are, right? So here's what we would describe a contraction in the index J, and so this diagram, so basically somehow highlighting one of the vertices as opposed to others. In this case, we represent it with a black dot. Actually, in the code, this will be the other way around. The black dots will be the free ones, which need to be more visible, and the gray ones will be the contracted ones, which effectively become part of the edge, as I'll show in a second. So this is how the contraction happens, right? So Einstein summation is not assumed here. We do it explicitly with our summation symbols, just to be very explicit. And then you can start to do some rough graphic calculus for shapes, basically. So you know that when you contract two matrices, you get another matrix out, right? When you multiply the matrices, so you get this kind of situation. When you make the incidence of two matrices, meaning you have two index objects and you multiply along one of the indices, what you get out is a 3-index object, right? Which is the triangle of all the cases in which the 3 indices are in that configuration. So anyway, so you have some basic calculus. So here you have some other configurations, right? Again, very messy looking formulas. If you try to read through this, like sum over PQ of this mess, like, okay, I'm lost, right? I don't have a good sense in which I'm reading like M, N, A, and so on. But this diagram has a much clearer perspective. You can see how M and U are disconnected, they're not going to interact, and so on. And it's much more easy to grasp at a glance, right? So anyway, the main point here, so of course, you can introduce identities, things that are just 0 or 1 in the usual sense, and they have a nice algebra, that when they combine in different ways, they all belong to the same. The idea of very familiar to a lot of physicists to introduce an identity somewhere, right? Like you say, hey, I'm gonna multiply and divide by the same quantity here or there, right? This is a feature of our graphic calculus. So for example, in this triangle, if you contract an identity to any of the vertices, you get the same triangle back, right? And similarly here, if you have, for example, this contraction, you can introduce a ternary identity among the 3, and it gives you exactly the same result as an array product, right? Okay, so this can be extended. We can do more things. You can recover traces and partial traces, and so for example, this is the trace of a matrix, right? So very, very conveniently in a graph theoretic way, traces are just loops of matrices with themselves, and you can recover simply the vector of diagonals. So this is just the vector of the diagonal elements. You can extract it, so that just looks like this kind of diagram here. And then of course you can take partial traces, and you can again, forgetting about the sequentialization of indices, you also can do this tensor product operation, which basically just means bundle everything up, right? Like put them side by side, consider their values independent, and you just put them together. So that means that you essentially merge all the indices into one bigger object, and so all you're doing is just multiplying everything together with no index adjacency, no index incidence of any kind. All right, so what's the upshot of this? So that's cool for notation, and okay, that's fine. But someone might say, yeah, we don't need notation anymore, or whatever. Like we're good with just doing the usual good old notation. So what does this bring us? Well, this allows you to perceive some of the algebraic properties of the algebras of these arrays in a much more transparent way. So let's say that we have two matrices, A, B, and we represent their multiplication by this diagram using our Plex system. Okay, so you would find this kind of pattern, and you would write AB in place where you compute the matrix multiplication. So more explicitly here with the indices, you have this. You can put the index names. So J here is sort of absorbed because it's a dummy index. If you can represent the orientation of the product, because this is just one. Basically, the anatomy of an edge allows you to keep track of a sequentiality of the product. And so, of course, if you have a triple product like this one, ABC, as I said, the anatomy of the edge allows you to keep track of the sequentiality, and so you can characterize it by writing it like that. So this, of course, generalizes to other products, and there's like this, which is the more or less famous Zapata-Carratalá product, and so on. However, what is the point? Well, the point is that matrix multiplication is the first non-commutative associative binary operation one encounters when defining these kinds of objects. And if one is interested, as we were, in generalizing the notion of associativity, or maybe not just generalizing, but really deeply understanding what it means for an algebra to be associative, and what it means to have these compatibility axioms that are somewhat natural, but sometimes are hard to argue why they are natural or where they're coming from. Well, in this particular context, they appear as a very distinct phenomenon when thinking of the way you operate these diagrams. So imagine that you begin with this, and you're only given this rule, right? You know that you only know how to multiply matrices 2 by 2, right? Like, I mean, what I mean is in pairs, sorry. So you take pairs and you contract them like this according to this rule. So if that's the case, then on this diagram, you can only apply it in 2 places, and you get AB on the one hand and you get BC on the other. But now, of course, when you multiply these together, you're going to get a single Plex diagram that is called ABC without the brackets. But of course, if we were keeping track of the ordering of the sequence of operations that we perform on our diagram, then the right-hand side will read A with BC, and the left-hand side would read AB with C, right? So basically, this is a way to identify that the associativity axiom here, this term identity, will have to hold for this diagram to be well defined. So that there is a single such thing as ABC in the end, and not multiple. So here's our thesis, basically. Well, we realized that the diagram had a few properties. So the diagram we began with had a few properties. First of all, we only used a single motif, although that's not essential. It was regular, meaning that it had only edges of the same kind. Again, not essential, but it was a feature. And crucially, there was overlap, right? So overlap means that the motifs that appeared in the diagram had some common edge. So here B, is seen by this rewrite on the right, and is seen by the rewrite on the left, right? So that is what we use as a premise to define generalized associativity. So we say that a product, in this sense, is generalized associative when you can find a diagram that satisfies these properties. So it's a definition that is indirect, right? So you're saying, I'm going to call this operation, which might look weird, like these kinds of things, like these kinds of diagrams, or some of these. You would say, I'm going to call this thing associative if I can find a diagram, which is going to be bigger than the actual pattern itself, where you can produce this confluent rewrite system where there was overlapping of your pattern matching, right? Of your actual motif matching. Okay, so that's a working definition. It's an indirect definition. It's nothing similar to what people do in logic and algebra, where they declare associativity as being one of the axioms, or as being one of the term identities that need to be satisfied, or like in operat theory, where you have the operat of associative algebras, and you have this encoded in this kind of categorical structures. Here, this is much more down to the framework, or down to the computational language, where you say we have now a kind of a grammar to express a whole bunch of products, many of which are very meaningless and very degenerate, and all these expressions are very equivalent to each other. Like all these products here, like these ones here, they're representing the same thing. Like this diagram, that diagram, they represent the same thing. It's not a unique expression, but they're certainly, once they're given, they're fully computable. You just run through the possible rewrites, and you get all the possible answers. So the definition of generalized associativity basically hinges on the fact that you can always compute with these things, right? These are always computable things. They are not just sort of rough representations. They are exact objects and symbolic, and they can be computed on. So, okay, so what is the application of this? So we know about associativity. We can replace the pattern with a longer pattern, and instead of just matching two in a shape of a V, we can match a chain of this, so basically a chain of matrices. So if your pattern is a chain of length m, so n matrices that are concatenated in this exact pattern, and you say, hey, give me a chain of n matrices where n is larger than m, then you will find some term identity by the same token. And basically the case n equals 2 and n equals 3 is the usual associativity, but you choose any m and any n so that n is larger than m, you would have a different term identity. So in a sense, one regards this as all being the same kind of associativity, because at the end of the day, all you're doing is just using a chain of binary edges as your pattern, and just basically saying that you can move it around a longer chain. So what is the surprising application? Well, it's when one is interested in investigating heap theory. So heap theory is this theory about ternary algebras that satisfy this axiom. So I'm going to make it a bit bigger just to be very clear that here you have ABCDE, here you have ABCDE. That's what you would expect from associativity, like above. But in the middle term identity, you have D and B in swap positions. So this is kind of quasi-associativity. It deviates slightly from associativity. And so, these were structures that were kind of known in some obscure areas of algebra, but hadn't really been very heavily studied at all. And so, but we were aware that there were some cubic matrix multiplications that actually had this behavior, that displayed this term identity. So anyway, so in the paper here, we give a summary of it. So we went to this paper and we found that there was an expression that basically corresponded to this diagram, right? So just to be clear, because we don't have it here, I'll go to the beginning. So remember, these Plex diagrams represent 3 index objects. So if this were a product that we found in some of these papers that identified some axioms, and then we said, well, under this perspective of Plex diagrams, we can represent this product like this diagram. Okay, so far it was just a way to visually track the product. There was no advantage there. But then the real advantage came when, we were, I remember Xerxes and I were in Barcelona in the seminar room, and at one moment, we realized, wait a minute, this fish shape actually contains more information than just visually tracking the indices, how to contract to compute it. It actually contains the axiom somehow. And so here's the beauty of the discovery. This is the kind of the most important discovery we've made. It's not very fancy, but it really is the kind of cornerstone of this approach, which is to say, well, now remember, what we want is a larger diagram in which you can find the patterns in a confluent way, but overlapping when they occur, right? So we thought of this long fish shape, ABCDE, in this particular fashion. And of course, as you can see, you can find a fish in 3 different ways. You can find a fish swimming to the right, then another fish swimming to the right, also a bit ahead, but then there's also a fish swimming to the left, right? There are 3 fishes inside of this big diagram. And so when you actually run the rewrite system, noting that the notation here is that tail, body, head is what defines the tuple ABC, right? In this fish here, you say, well, this is what I mean here. ABC is defining a tuple ABC but by looking at the positions in the quote unquote fish anatomy, right? So the first element of the tuple is the tail, the second element of the tuple is the body, and the third element of the tuple is the head. And this is well defined because this particular hypergraph has enough asymmetry so that these things are kind of topologically well defined. So if you take that perspective and you go into this diagram and you take the rule that every time you see a fish, you rewrite it as a single triangle with that tuple inscribed, when you end up with is precisely this diagram, right? You find the leftmost fish, the middle fish, and the rightmost fish, and you get these 3 fishes again, which is a very good sign because it means that we are going to be confluent to a single triangle in the end, just like in the case of binary, in the binary operation of matrices. But very crucially, the tuple that you would write in the middle here is in the reverse order, right? Because ABC is a triangle ABC. Here, CDE is a triangle CDE. But the triangle here in the middle is kind of flipped. So it's kind of like we're looking at it from the other side of the piece of paper in this particular graphic. So we express it that here, right? Like we say that, you know, if you put it in the same orientation, this thing has to have this sequence, so that when you consider that all these three fishes actually compute to a single triangle in the end, which is one single cubic matrix with a single value, right? We know it's going to be confluent because it just is one single object, but it has three different names. So the three different names are precisely the bracketings of the semi-heap algebra, right? So that was the discovery, basically, that by doing the fish pattern rewriting on this diagram, we rediscovered the semi-heap axioms, and that was a big surprise. And so that's what led us to the definition of this. So anyway, that's basically the content of the paper. So after that, we go into some a bit more technical things where we find some sub-algebras of these semi-heaps, and we relate them to each other. We try to see if there are units for these things. So meaning, you know, what a unit is. Let me see if I can find a formula for you. Not here. Yeah, so what a unit is basically something like this, right? Something that would cancel out. So you have an element and it's maybe inverse, and by multiplying them together, you maybe get something like the identity matrix, right? Like what happens with matrices and their inverses. So here's a bit more complicated because this is not, you know, you're not multiplying just a matrix, you're multiplying two cubic matrices, and you can multiply in several ways. So anyway, so there are some options here. We find that there's indeed some partial identities and whatnot. So, but yeah, general problem still open how to find all the possible units there, and then we connect to previous results and so on. So that's basically what we do in this paper. So I'm going to show you the notebook implementation of this. So these Plex diagrams we actually currently have in this form. So you can simply specify, let me increase the zoom a little bit. So you can simply specify the indices that you want to contract, right? So here, we just have a matrix multiplication, right? So I want to show you that that's just, where is it? Here we go. So this function over here, a Plex product, takes a hypergraph with.
Turn the paper colors.
Oh, I'm showing. Oh, sorry. Yes, I thought I was showing the screen. That's very true. That's very true. Screen. Apologies. Sorry. So I was trying to show that this Plex diagram formalism is now implemented in Mathematica notebook. So basically, what you can do over here is you can specify a collection of indices and a collection of contracted indices. You can also specify what kind of symmetry you want for your diagram, and this produces a hypergraph object in our current hypergraph packlet that, I mean, as a Plex diagram, as it is implied from the paper, it's just a representation. It doesn't have any functionality built in, but we also have a function here where we can turn it into a product. And so, as you know, in Mathematica, this dot is just dot product. So this is just matrix multiplication. So I generated A and B and ABC, X, Y, Z. These are arrays of the right sizes, right? So X, Y, Z, UV are three cubic matrices, A, B, C, D, E, etc. are two matrices and things like that. So you can see that just by specifying this Plex diagram here, which is just, you know, the V pattern, and applying it via Plex product to any two given arrays, I actually get the matrix multiplication. So that's one way to see what we're going before. And so here, similarly, we have the fish product, right? And for example, we can show explicitly the semi-heap axiom, right? So you take Plex product of X, Y, Z, and then together with UV, that's the same thing as Plex product of X. And then inside you have U set Y, so you're flipping the Y and the U as you saw in the paper, and then V, right? So we check this is true. So we have an effective, you can compute with the fish, right? Here's the fish, and you are acting a fish on a set of arguments. So you get that functionality. But we also get other products. The most important one, of course, being the Zapata-Carratalá messenger. So conveniently, here you have the order of arguments in which this will eat its arguments, right? So when you take the Plex product of this alpha, beta, gamma, alpha will go in the #1 and beta will go in the #2 and so on, right? So it's usual slots, just in the graphic representation. And so you can check other things. You can check like symmetry of these products. We can check the properties of partial identities. So these identities are, capital ID is the ternary identity, so it's just ones in the diagonal and zeros everywhere else. And I, R, I, G, and IB are what we call the red, blue, green partial identities, which are basically amount to stacking identity matrices in the three different directions of the cube, of the cubics they form. They are technically a broadcast of identity matrices in each of the three directions of a cubics, right? So you can check some of these neat identities that the identity cubices form a subalgebra. They close with themselves. All the tri-identities give a tri-identity. The red identity gives a red identity, and so on. But we call them identities not just because their elements are zeros and ones, and they are like some kind of generalization from the identity matrix. Is that because they actually behave like neutral elements for the algebra? So you can see that for this particular product, if I take alpha, which is a generic cubics, and I fill in alpha as the first argument, and then green, and then blue, this gives you alpha as an output, right? So it acts as a neutral element in that way. So anyway, so those are Plex diagrams. I am still working on having so for example, I'm working on enumeration of all possible Plex products that can exist, because naturally one wonders about which are the ones that we are missing on, right? Like we might be missing out on some cool algebra that is a little bit more complicated than just matrix algebra, but it's still understandable by a human mind, right? Obviously, if we have to do with like 27 arrays of like 50 arguments, that's not gonna be comprehensible by a human mind. But it might be that something to do with ternary arrays that is just ternary or a bit higher, that might still be like manageable for a human mind to comprehend. And so, for example, here, this function in Plex product enumeration, what we are doing is simply first enumerating all the simple unconnected hypergraphs of the right distribution of edges. So in this case, if you want a ternary operation with QBCs, with ternary, so 3 index arrays, then what you want is a hypergraph that essentially puts 3 ternary edges in all possible configurations together. And then once you have that, what you want is, remember, here I am expressing, by the way, it's the opposite convention than the paper because it is better, I think, visually. So the black dots are the free indices, right? So the body of the edges is gray. So everything that's gray, it's not an index, right? It's not a free index. So that's kind of the visual logic behind this design. So obviously this is just preliminary, but the point is, these are all the ways in which you can contract any number of indices in your expressions so that you get a 3-index expression in the end. So what this function does is, first it lists all the possible diagrams. So it lists all the possible hypergraphs, very similar to doing this. So hypergraph, enumerate hypergraphs. If I just give it, I don't know if this works. Oops. Has to be on this. Nope, I have to say all. So it first enumerates the right skeletons where you would write your cubic matrices, your arrays, and then because you are demanding for these things to be products, meaning that you input a collection of same kind objects and you get the same kind object out, it's going to basically enumerate all the possibilities for index contractions within that diagram, right? So, for example, when let's use this as an example, right? Enumerate Plex products of binary to arrays, right? So actually the other way around. So this is two arrays and we want binary operations of two arrays. So if you're wondering how many ways can you, given two matrices, define a product that gives a matrix out, a well-defined matrix out? Well, there are three ways. Really only two, but there's technically three ways if you keep track of the sequence. One is to, you multiply you do basically Hadamard product on two of the matrices, keeping one index in the middle. So that's a 3-index object. And then you contract the index in the middle. What's that? Well, that's just matrix multiplication. So this pattern here is just matrix multiplication, right? But you could also take one of the matrices, contract one of its indices so that it becomes a vector, right? So basically contracting one of the indices means doing kind of row-wise addition or column-wise addition, right? So I don't know how people in the sort of machine learning call this, right? But when you do this kind of partial traces, right? You know what name they use for this, like doing the
Partial tracing? I don't know.
It's row,
I would-
row-wise and column-wise.
yeah, row-wise and column-wise.
or just
I
array reduce. I don't know. Doesn't
So
have
yeah, I
just
mean,
remove.
taking the sum of the rows or the sum of the columns and collapsing a
Yeah.
matrix that way is sort of it's like you're taking a dot product with a constant one vector,
Yeah.
and it's either like on the left side or the right side. So or it depends on which index you choose to collapse with a constant unit vector.
Yeah. Well, anyway, but the operation is
dot.
clear. Yeah. That's yes. So the operation is clear. It's basically you're doing row-wise and column-wise addition.
So is that what the dark dots are, or
No, the clear ones, the gray ones, are the ones that are not indices, right? So they are contracted away.
okay?
So a gray index means that on that index you're gonna sum, right? You're gonna sum over all the possible values.
If it's dangling, I guess if it's
It's the same actually, because
so it's contracting itself, I guess is what you're saying.
that's one way to put it. Contracting itself when it's a single dangling vertex, right?
Mhm.
So I mean this was quite clearly shown in the paper. Let me just. So this case was over here. Yeah, so these operations, let's see. Right. So this would be the example, right? Like, remember, like a single node means that you have one index vector, right? I'm sorry because the convention here is flipped, right? Like what's gray is not contracted and what's black is contracted, and it's the other way around in the notebook. But basically you sum over the index, whatever it is if it happens to be an index that is shared by many arrays, then you're going to contract those arrays because the index happens in this distributed fashion, right? Oh, what happened here? What the hell?
What is something wrong?
I don't know. Anyway, but yes, so there's an enumeration of hypergraphs first, and then there is all possible distributions of, I mean, it's very intuitive because what you want is you first draw a hypergraph, so no black nodes or gray nodes, and then you distribute as many black nodes as you need to have only 3 remaining nodes, right? So it's a very straightforward function to enumerate because all you do is you count the total number of nodes, and you basically subtract the number of nodes that you need as your output shape, and you basically put that number of contractions in all possible locations, right? So for this case, the binary case, you have matrix multiplication is one option, and the other option is to first collapse the matrix into a vector. This is what I call flattening, but whatever. So collapse the matrix, one of the matrices into a vector, either columns or rows, and then that is a vector. So then you can multiply with a matrix, and we know that matrix. Wait, what am I saying?
Yeah,
So,
that may be a little tricky if you first collapse and then multiply, because algebraically, what we are doing over here is if you have I, j, j, k, we are summing over the I, keeping the j fixed. So it's important to do it so that's why this thing that Dugan mentioned of first multiplying one matrix with a identity column and then multiplying to the other is not exactly, may not exactly be the same thing of what we are doing here. The I, j, j, k, the I is summed, j is fixed. So we are using the structure. We are not first collapsing the matrix. We are using the structure of both, but in this different way. That's what this is.
Yeah. So exactly. So what's happening here is you're multiplying. It's very easy to follow when you know that the formula here. So I'll just
maybe just show the notation.
Yeah.
So that it's easier.
So here the notation would be, you begin with your A1, which is white. You begin with an A1, sorry, an A and a B. Just say have A and B, right? Each of these are going to have 2 indices. So the fact that they fit into a product diagram means that they're going to have 1 index in common. So without loss of generality, I'll just call I, J, J, K. And of course, there's reshufflings of sequences of indices, but for this just counts the topology of the products. And so these 2 indices are assumed to be common. So one in each is common. And so the question is, where do you contract? And you can only contract in one place because we have 3 indices. The total, the total thing has IJK indices, right? So as an object, we can only contract in one place because that would, what we want is a 2 matrix out. We want the same kind of object out. So if we contract on the J, right, then we get matrix multiplication. That's the usual formula because, I would write it like this with J like that, and that's matrix multiplication as we know it. But if we contract either on the I or on the K, which is symmetrical, basically, it's either rows or columns kind of thing. So let's say we contract the I. What I'm doing here is I am summing over, I'm taking this 3 index object and I'm summing over the I, right? So it's basically an operation that affects each component, and you have a cubic object, and what you're doing is you're collapsing one of the dimensions and you're flattening it out to just be flat, to just be a matrix, right? Instead of the other operation, which actually corresponds to doing some kind of pattern matching. So you're basically saying, do you have a 1 here and here? If yes, then you have a 1 down here, right? This other one is just ignoring the other 2 indices, and it's just basically saying, do you have a 1 at all in this column? If so, you get the result. If not, you get a 0, right? And so it's basically two ways of flattening: one that doesn't care about the other indices, and one that does care about the other indices. So in the binary case, it's kind of transparent, because if you have two matrices, you form a cubics out of having one index in common. There's basically only two ways to bring it down to again a matrix. But when you go into one step higher and you have three matrices, three cubic matrices that can produce a cubic matrix, then suddenly the possibilities are much larger. And these are many of the examples, right? So you can have this kind of diagram. Really, there are many isomorphisms here, because up to reordering of the indices, it doesn't really matter where the black dots go, as long as the topology is the same, right? So for example, this diagram and this diagram are topologically the same, right? They are technically distinct, as so if you have the same size of arrays, this will operate to different values, but you could always rearrange your arrays so that they operate to the same value. That's kind of the logic there. So yeah, there are many products here. So as you can see, this is the ternary analog, right? So it's a big world of possibilities already, and so one of the reasons why we wanted to think about this generalized associativity definition was that, how do you even make progress with all these operations? Like, what are good questions to ask these animals? Each of these things, again, up to reordering, but even if you just discount the dotting, there are 9 different shapes in this list over here. If you disregard the combinatorics of the black dots, there are 9 different shapes. So how does one go about understanding the different shapes and what products they define and so on? It's not obvious. So that's why we decided to come up with a procedure that would try to extract these properties, right? So anyway, that's basically what I had to say about Plex diagrams. I don't know if you guys have any questions, or there's anything. Actually wanted to go to YouTube and see if there are any audience questions or anything. Oops. Yeah. Right. So hello everyone in chat. I just opened the chat here. So yeah. Anyway, this is now implemented. We can do searches. We can do some experiments. So as many of you have seen already, like this notebook of mine, these are possible generalizations of this pattern. So basically trying to recover the same sort of structure. So here the fish composition is the one that I've shown you, where we are just now operating symbolically. There are no arrays involved. These are just symbolic diagrams. So these are, like in the paper, purely notational, but we are able to really abstract the process and say, hey, I give you the label diagram, you give me a non-confluent system. This is just a tree of rewrites, and you get to 3 different places. The same triangle 1, 2, 9, but different names, because the bracketings are different. And so the key is, if you unlabel this diagram, so it's the same as above but unlabeled, and you run the system, now you get a confluent one. So you say, hey, there might be something non-trivial here. So you run this branch of graph thing, and you might see the fact that these 3 patterns are actually overlapping. So for this, I'm working on a function that is going to show it more explicitly. But we are interested in seeing this pattern beyond this, right? So for example, this one has a similar behavior with this starting point, where when you unlabel, you get something quite neat that just shows the evolution, but it does not correspond to any algebraic phenomena, because there are no overlapping patterns in in the original diagram, right? So all the overlaps are sort of partial. Oh, so there's a question whether I can show a short numerical example for the Plex diagrams. Sure. Let me. Yeah.
Yeah, I was thinking because the examples you were showing with the two matrices going into a three arity structure, cubic kind of thing, would be interesting to visualize with like 3D plot.
Yes, that's
3D image.
Let's do that. Let's do that. So, let's define let's define the Plex diagram with. So what is the idea? The idea is to have two matrices operate into in the most basic way. So no contractions, only incidents. So how many ways can you incidence two matrices? Well, 3, I guess. No incidence, partial incidence, meaning one common index, or full incidence, which is two common indices. So if we have full incidence, that's kind of boring because it's basically having two matrices on top of each other. It's just kind of two copies of the same thing. But and no incidence is kind of boring because they are just separate, right? So the partial incidence in the binary case is really minimal because there's only two matrices with one common index. So let's begin with one common index. That means that I will have one matrix with indices 1 and 2, and one matrix with indices 2 and 3, let's say. And I'm going to say no contractions, right? So this is the shape of my diagram over here, right? I have one thing that operates to another thing. So let's do the Plex product. So let's define two matrices, 2 by 2 by 2, for example. So let's define A. Let's do a different some different names. What names? Well, actually, let me just show you what A looks like and what B looks like. Right? So these are just 3 by 3 matrices, right? So right? That's just A and B are just two 3 by 3 matrices. So what happens if I do this, right? If I do Plex product, this thing of A and B. Oops, that should be a comma. What is this thing? If I do matrix form of this, maybe. Right. So as you can see, this is a matrix of vectors. So it's a cubic matrix, right? So that's the starting point of your operation. You have two matrices. The most minimal operation between, well, I mean, the most minimal. Intuitively speaking, the minimal thing that you can do is you can say, hey, check if for index I, index J, and index K in this pattern of this diagram is giving you a pattern, right? How many of these things do you have? That's a question that you ask for 3 nodes, right? Sorry, for 3 indices. You're asking index I, J, and K, whether there is a value, a non-zero value from A from I to J, and then a non-zero value from B from J to K, right? So that's that question that involves 3 inputs, right? I, J, K. You specify what are the I, J, Ks, and the question is asking, do you have the first matrix in between I, J, and the second matrix between J and K? If the answer is yes, you get a positive value, or as many values as you multiply in that location, and so on. So the answer to the question is a cubic matrix, right? Because it's something that has some values when you specify 3 indices, I, J, K, right? But what happens when, so with this cubic matrix, this cubic matrix, by the way, contains all the information necessary to operate the matrix multiplication. And in fact, I am aware of Oh yeah, WWKK. Yeah, thanks for the feedback. I'm glad that this was useful. So, by the way, this is what people working in matrix multiplication optimization use a lot, right? They often, when you're about to perform a big matrix multiplication, there is otherwise just plain old matrix multiplication, but the objects involved are huge. It is common to generate these larger tables that require no no searching. This is basically just listing all the possibilities, all the numbers, and then performing some operations on this tensor, on this larger. This is a 3 by 3 by 3 array, right? That 3 by 3 by 3 array contains all the information you need to compute the matrix multiplication of A and B. But you have to do something specific to it. What you have to do to it is that you have to sum over the middle index, which corresponds to doing exactly what I was describing, which is, do you have at least one, or how many thereof of these patterns of ij in the first argument and jk in the second argument, right? So this is partly the power of these Plex diagrams, is that, if you were to try to develop an intuition of what the computation is about just by looking at a cube of matrices. And by the way, do I have the cubics here? I think I have the cubics. No, maybe I have it over here. No, wait, I do have a real algebra open. No, I don't. Right, so I think I do have it here, yes. So, this is the kinds of objects that we're working with, right? So these are visualizations of these kinds of arrays. And if you were thinking of these products, this is exactly what it's doing, right? It's taking 3 of these guys and it's giving you another one of these guys. So it's kind of difficult for our brains to wrap our head around it. Right? It's difficult. It's like, just what is exactly going on here? I'm not sure. But when I tell you that all that's going on here is actually that you have this diagram being applied to the indices, that's much more transparent, because that gives you all the information you need. You say, okay, right, so I put my arrays in the right positions and I get the things out. So anyway, I hope that clarifies a little bit. And unless there are any pressing questions here about this, I have one final thought to share, and maybe we can riff on it a little bit, see what you guys think. So any other thoughts or questions about these Plex diagrams? Like, what do you guys find interesting about it? What is your stance on these things? Like, how do you think of these objects? Like, what is your reaction to this, basically?
Well, I think of them as just a nice visualization and perhaps generalization of Einstein summation, like functionality, like other frameworks in programming languages people using when you just want to contract their tensors, or maybe they have just specification of tensors as a bunch of indices, and then you want some indices out of that. And they usually like specify it with a string, right? Well, that's what you do in the programming language when there's also strings, but here is just a visual presentation of the same kind of.
Yes. At that level, it's very, very similar to that. Like, there's obviously, we have the extra algebraic interest of understanding this behavior with more of the rewriting, but yes, the system itself is just a visual presentation of tensor contraction. All right, so that being said, I'm gonna show something that actually goes beyond the usual tensor contraction algebra, and you can tell me what you think. Let me join with my applet. Okay, so yeah, we can all see this, right? So what am I thinking here? Okay, I have been talking about these Plex diagrams in a way. Let me not spoil it, just to keep your minds a bit clearer. So we've been thinking about this idea that, right, if you express your arrays or matrices or cubic matrices or tensors or whatever with some kind of graph diagram, hypergraph diagram, there are some niceties about it, right? Like we have some affordances kind of natively in the hypergraph language. And so what I wanted to try and implement now, because so far, as many of you might have noticed, is that indices are completely structureless, right? They are just plain indexing kind of indexing elements of a list, right? They have no structure whatsoever. But obviously, if you come from differential geometry or from linear algebra and all the tensor algebra in general relativity and so on, you know that indices usually have two kinds. You can be covariant or contravariant, right? Like these things are not just indices anywhere. Of course, there are simplifications when you have a metric around and you can lower and raise indices and things like that. But from a formal point of view, mathematically, indices come in two kinds, in covariant and contravariant, and this effectively amounts to input and output in terms of string diagrams and things like that. So I was trying to think, okay, how would I kind of enhance the Plex diagram formalism? So imagine that you like the Plex diagram, like I do. I mean, I created it for a reason, I guess. And imagine that you like it enough that you say, it might not be perfect to express something like covariant contravariant composition, but let's try to push it. Let's try to take it somewhere where it might work. So so how do we express covariant and contravariant? So of course you would say, oh, that's easy. You just introduce a sequence in your internal to your indices. So basically you give an orientation to your edges, right? And okay, that's fine. But actually, even if you want to give an orientation to your indices and you had, let's say, a tensor from general relativity, like the Riemann tensor, the Riemann curvature tensor or something, that is a 1-3 tensor, right? You have to say, 1-3 means that you have one upper index and 3 lower indices. I mean, let me just write it here, right? So if we have something like this, we have this kind of tensor. You can say, right, it's enough to try and somehow introduce some kind of sequencing within an edge. So here you would like to say, well, just imply that I, J, K, L go in that order, and then that's kind of clear because you somehow magically remember that the first one is upper and the others are lower or whatever. But of course, that's not sufficient. You would actually have to say something like, I is kind of a upper index or input index, and then J, K, L, which might need to be in some kind of sequence, are kind of outer indices or output indices or something like that. So there's something going on that needs to be implemented, right? So imagine that let's constrain ourselves to only use undirected diagrams for now, right? Imagine that we are just trying to mod out all the sequencing kind of combinations, and let's try to make sense of covariant contravariant indices simply with labeled undirected hypergraphs. That's the game. Let's try to make sense of covariant contravariant indices with only labeled undirected hypergraphs. So my suggestion here is that if you want to compose, let's say, two matrices A and B, that they share an index. So P is a common index, right? But remember, indices are things that would just be living, around your kind of array space, and arrays themselves will be things that live between them, right? Like that, or maybe like that, and things like that, or maybe on top of it, like a unary and things like that, right? So those are the indices. So when we write something like this, A, B, I, P, P, J, we say that, we have I, P, and J, and we have, A is over here. Sorry. We say that J, A is over here, and maybe B is over here, right? That's B, and that's A, right? That's what it means to say that. So what if we wanted to express covariant and contravariance? Well, basically what we know is that there's two kinds of indices. One is a covariant index and the other is a contravariant index. So let's use our coloring convention. Let's just say that, you know, your A might have a black index and or a white index. So in this case, A is a 1-1 tensor because it has I as a black and P as a white. Okay. So what would it mean that for composition to demand this conformality condition that you only contract covariant with contravariant, like we do in multilinear algebra? It would mean that you will be generally looking for this kind of pattern, right? That if you have two kinds of nodes, and we can only compose when the nodes are in opposite coloring, so to speak, right? So this would make perfect sense because, you know, if we have this constraint, we then use the exact same Plex formalism as before, where we draw the diagram like we did before, but now the coloring is implied on top. So A actually has this white node, and B has that black node. So on P, we have the white A and the black B. So we can conform, and therefore we can kind of lock them together and compute A times B with the usual formula here, right? So anyway, so this is just a kind of funny way to just do the same thing as we do in multilinear algebra of upper and lower indices. Like, note that it is interesting that we can already see a difference of another product that is actually the same as the fish product, by the way, if we change our patterns a little bit. So instead, so we use the exact same objects, right? Like we're using black and white dotted lines of a graph, right? So binary edges in that sense. It's the same kind of objects. It's kind of lives in the same universe. So the same two patterns, black and white nodes. But now the composition is going to ask for a different conformality condition, which is that instead of matching different colors, you need to match the same colors, right? And well, if you do that, you end up with this expression, you know, this kind of diagram where P and Q are common indices, but are common only when black and white are assumed. And if you actually write this out, you get this formula, which turns out to be a semi-heap multiplication. Why is it a semi-heap multiplication? Well, because this formula over here is, you know, A times B matrix multiplication. This formula over here actually corresponds to, as you can see, I mean, you can read off the indices. It is I, P contracted with P over here. So P is actually in the other position of the usual contraction. And similarly, Q here is in the other position. So I would just have to transpose P, B in the middle so that the indices are in the right position. So I'll just write this like that. And to make the indices work, I'll just have to have a transpose in the middle, right? So this product is actually this. AB transpose C. So it is actually, as a ternary operation, it's a combination of a binary and a unary, because you have your binary matrix multiplication and your unary transposition. But as a Plex diagram with colored nodes, it just is a ternary operation. There's only a difference in the coloring pattern. There's no difference in the fact that you just have a ternary operation. All right. So anyway, so this is kind of my preamble to say, it makes sense to do this. You know, we can actually find constraints to find the products that we care about, and with constraints that make sense, right? So then my proposal is then, well, what happens with the ternary ones, right? Like we now have a different kind of situation. Well, in my opinion, the thing to do is quite obvious. What you would do is you now have, you know, your basic objects have three different kinds of indices. So naturally, you would assume a pattern that assumes that there are three different kinds, so RGB, let's say. And whenever you want to make a composition, you you demand that they are exactly incident in all these combinations. So let's say also that you always can do same color with same color, because that's kind of like, you know, doing a Hadamard, that you can always do it in your space. But if you're multiplying things from different spaces, you require this condition that things need to be in what we would call a triality, right? In the same way that you would say that covariant and contravariant can be contracted because the dual space of a vector space and the vector space are in a duality. Here, you would say something similar, you know, like the indices ijk, the RGB indices are in a triality and you can contract them together. So what's interesting here is that if you just tell me, okay, I want that pattern and I have this three colors and you give me 3 triangles, there is one natural diagram that you can draw that fits into this, right? So in here, note that I would make B, so A, B, and C coincide in the indices that are implied by this pattern over here. And note that I begin by not coloring, you can begin by not coloring the vertices at all, right? You just say, I have A, B, and C, and they have indices, you know, IJP, IPK, PJK, which means they have 3 indices in total, but 4 indices in total, but one of them is shared among the 3 of them, right? That's basically the description of this. And then you say, each of the objects is going to have 3 different typed indices. And this is just completely arbitrary. However you want to put RGB everywhere, you just throw it. But obviously, you know, if an index is called the same, then you have to keep consistent whether that's red or blue or green throughout. So if you have that, it turns out that if you want to build a shape, so a diagram that has just remaining indices, the RGB, like in the same way that the remaining indices of these constructions were black and white in the extremes, right? So the middle ones are kind of contracted together in this generalized sense. Then actually this is the only way to do it. It's kind of neat that you know, you have a lot of different diagrams that you could in principle multiply if you don't care about how your indices contract and how they fly around. But this is the only way to do that. I mean, we still need to understand what it means to make these constraints, but the constraints are quite obvious and simple to express, and the answer is unique, right? So why is that? Well, notice that here, pick any one of these triangles, pick B, for example. You can see that B has a red, green, I mean, you have to zoom in, kind of like green and blue, right? And then similarly, A has red, green, and blue. C has red, green, and blue, right? And they lock just perfectly in this pattern. And so this, of course, corresponds to the Zapata-Carratalá operation. So the index expression has this shape, and you know, in the literature, this is what a lot of people consider to be the direct generalization of matrix multiplication for arbitrary sized tensors, right? Larger than n by n, right? So n by n by n by n, etc. So anyway, this is what I've been thinking about, that it might be possible to you know, generalize a theory of covariant contravariant indices with this kind of, you know, port graphs kind of thing, where you have this extra condition on the contraction operation on nodes, right? You have this added constraint that your inputs. So by the way, the way to think about this is that you think of your product as a placeholder kind of thing, or like a template, right? So if I give you that, I give you this formula, you know, this expression, what you should be seeing is something that looks like, you know, you have 3 triangles somehow in this shape, right? And they are like missing exact inputs, and then you have your, like, the objects that you operate in your algebra are these things that are like kind of floating around, and they have their names, you know, attached to them, and they have their colors naturally. And so what you do is you try to fit them into this kind of template, and they only fit in when they satisfy this kind of canceling conditions, just like in this case, right? That A and B, you know, because A and B need not be square matrices, right? You can only multiply matrices in the right way, in this conformation way. So it's not just about the size of the index of the indices, but also how you order them, and you make the tables out of it so that you end up with a correct size of the table. So the analog in this framework would be that you have a template, and you can only fit things that actually have the right conformality. Now, the added layer to all this is that you can use this generalized multilinear concept of triality, duality, etc., by imposing this kind of coloring constraints. But anyway, this is speculation at this point, because it is clear to me that there is something about a triality going on here. There's something, triality-like in this product, but it's not obvious to me at all what exactly the theory should be. Because mathematicians are kind of confused about this. Like I talked to many of them about these things, and we are still confused. So this is just my latest attempt at clarifying that. So anyway, any thoughts on this?
So why is it constrained to be like in the center having all three colors? Why is it the only way to constrain this particular composition like we had above with the binary case?
No. I didn't say it's the only way to constrain it. I said that once you assume this constraint, this is the only diagram that you can draw with that constraint.
Okay. And for if you choose like two colors like blue, red, there are more than one.
Oh,
Right.
absolutely. Yes.
That's what I meant.
Yes. So for example, you can imagine, and something that I think will be very natural is that you not only have, so for each RGB, you actually have kind of like light red and dark red, right? You have light green and dark green, and light blue and dark blue, and so those are dual to each other in this binary sense, above of covariant and contravariant. But then they are also in triality, right? So you would have like contravariant indices RGB that are kind of in triality and so on, right? So you could have this, and so actually I haven't tried this, but you could imagine that because technically, A and B in this diagram, right? A and B share a index there, right? They are overlapping, right? They're sharing the same index I. So technically that's not a rule here. I mean, that's technically, like the red in here, the red is like from that side and from that side, right? Attached to B and attached to A. So you could just make it so that A and B are in that index, one is covariant and the other is contravariant. So, they have this black and white coloring underneath as well. And so you make that pattern work. And I believe that is possible because if you have this, I mean, you just need to like label it with some kind of, ooh, why is this so large? So you can just label it with, yeah, right? So dark light, dark light, dark light, right? So you just order things in such a way that they, when they meet at the extremes, these things are, dark red with this particular combination. This would be a possibility, right? But you couldn't have light because you cannot contract two covariant indices together naturally, right? So anyway, it's just a hypothesis here, like kind of entertaining what this.
So is it like some kind of this ternary analog gadget for a metric that allows you to swap around your indices, because you not just have like covariant and contravariant, you have something else, right?
Yes. So right. So the analog is that, when you are in a vector space, right, and suddenly you introduce a basis, over the reals, this turns the thing. So this is basis. This turns the thing into Rn, right? And so you can define here a particular operation. You take v.w and you just sum this thing, right? This is the usual dot operation, the dot product operation, but there's no metric around. You just decided that you wanted to put the two things together. So that exactly corresponds to this covariant contravariant contraction, right? So of course, all you can do is you can now multiply three things together, right? You can do this thing. No one's stopping you from just writing the same formula, but with three, right? So that thing over there corresponds to this triality contraction, right? It is kind of like a ternary dot product in your space. And in fact, we studied it a little bit algebraically. We know that it's not like you can compute the values of this thing by knowing the dot products of the pairs or anything like that. Like it is a fully independent trilinear form in your vector space. Furthermore, for those curious, this thing has no symmetry group. So if you ask what elements of the GL group, the general linear group, so these are all the invertible linear transformations of your vector space, what preserves this? So we know that, when you do the GL transformations, GL stands for general linear, right? So invertible linear maps. Here you get orthogonal transformations. So these are the isometries, right, of your Euclidean space. But if you do GL here, all you get is Zn, which is just the permutations of your arguments, which because the thing is symmetrical. And so really it's empty, basically. There are no symmetries. So if you ask what transformation of your space conserves this quantity, there's no transformation other than just reshuffling of indices. So
that's interesting that you get a discrete group out.
Well, it's not so interesting because it's not so interesting. So
it's
it's essentially the same as getting the empty group. Sorry, it's not empty. It's just the trivial group, right? I mean one, right? So it is as interesting as the trivial group because the set M. Actually, this is not true. It's not. So
I mean, it has the identity, but then it has right.
It says sorry, it's Sn. It's just because you have full symmetry of your arguments, right?
Mm-hmm.
What am I saying? It's S3. It's three arguments. That's what it is. So it is very weird. I mean, the fact that it doesn't have any full symmetries, it is, in a sense, intuitive when you think about the product, what the actual product does, because one of the things that you can check, it's kind of funny because one of the things you can check with the binary one is that the value of the dot product, in a way, it is clearly invariant under reflections and rotations and so on. In particular, you can intuitively think about the axes of your coordinate system are signed, right? They have a positive side and they have a negative side. So the fact that when you move around in your space, the signs of your coordinates are going to compensate in a way that the dot product always has the same sign, right? Because it doesn't change sign by rotation because it doesn't change value. So so that's absolutely not the case with a ternary one. The reason being that when you do -1 times -1, that's always +1. But when you do -1 times -1 times -1, you get -1 again, right? So your degree is not natural to this idea. So what you get out of this is this cubic. So another question you can ask is, this dot product, the binary dot product, defines a distance that defines the Euclidean distance in your Rn.
So do you recover negation along an axis in degree 4 arity 4 product?
You mean if I define the for RE1?
Right.
Like this one?
Mm-hmm.
What is the question?
When negating an axis, they'll maintain that sum.
Does it? Isn't- I guess so, right? Because you get. Yes, that's right. I think so. Yes, yes,
Yeah,
yes,
yeah.
it does. So, yeah. The reason why I've looked into the ternary one and not the quaternary one is because I believe there is some priming phenomena here, right? Like clearly 4 is 2 times 2, and 2 plus 2. So, so I think that is relevant in this case. 3 is not 2 in any way, right? Arithmetically speaking. So, I mean, 2 and 3 are primes and co-primes in particular, right? So, so I think that's what's going on. So it is a very weird thing. We don't have any good ideas here. That's why I'm trying to, go to kindergarten and start drawing like funny colors instead of like doing any serious mathematics, because like this realm of structures becomes strange. Like, if you suddenly like imagine you go back to high school and you're in class and your teacher for some reason just decides, they have a pretty bad hangover or something, and they write 3 arguments for the dot product in the blackboard, right? Like they just go and like, okay, 3 arguments, and you go home and you take this as the gospel, and you just learn geometry with 3. It is pretty difficult to imagine what you get out of it, right? Like, so basically, what I mean by this is, what are the natural things that you get out of the dot product? Well, it's the usual constructions of Euclidean metric space in Rn, right? So you get the distance, you get the angles, you get all these notions. So in particular, you get shapes like the sphere, and the quadratic surfaces, all the conic surface, all these things you get out of the dot product. And if you ask the same things for this ternary dot, you get weird things. You get, if you ask about what is the ternary sphere, right? Which looks, in the plane, it looks like something like this, right? That's the ternary circle. So that's not a very nice curve, right?
No,
I mean it's a curve,
like hyperbolic almost.
yeah. So these things have like multiple branches. They have these kinds of shapes, where in the plane these are the axes. You get things that kind of look like that sometimes, but they also look like, my favorite is when the thing looks like something like this.
Mhm.
It has some like weird shapes, right? It gets pretty strange. And I think there's a degenerate one that's quite funny because it looks like this basically. So these are surfaces of like equidistant points, right? I mean, it's very strange. Like it clearly doesn't really correspond to these kinds of things. So I don't know. It is difficult. I don't know. I don't know if the theory of triality and ternary dot products and so on only makes sense. So one of the problems here might be that we are doing this in this context, right? Where our coordinate axes are specific algebraic structures, right? These are fields, right? These are pretty strongly behaved rings, right? So it might well be that these notions only really start to make sense when you generalize your scalar fields. That sounds like physics, but what I mean is when your scalar values are a bit more generalized, and maybe they range over semi-rings that are non-commutative, for example, right? In those cases, then things start to make a little bit more sense, perhaps, because you no longer have this notion of interpreting geometry like equidistance and things like that, right? Like it loses that geometric meaning. But then you also lose the kind of intuition of what you're doing. And you get into further exotic mathematical territory. So it's not particularly useful. So anyway, so that's why I kind of abandoned this line of research. I mean, meaning the purely algebraic one. But I think this one might make sense, right? Like I find it much more approachable to say, hey, we have a pretty good grasp of Plex diagrams now. We have good tools to enumerate, to check for associativity-like properties with this confluence, rewriting, and so on. It seems to be natural to say, well, let's try to build the theory of duality, triality, and so on top of this framework, right? To me, it's the natural thing to do because, my philosophy is Plex diagrams have helped at understanding the algebraic behavior of array algebras better. I mean, well represented with a fish product and that pattern. So might as well try and generalize as much as possible the behavior, sort of the index kind behavior and the covariant contravariant behavior, and on those as well. So, oh, WWK, that's absolutely correct. That's I love that comment in the chat from WWKK. Says yes, the other day Gabriele Carcassi was not understanding Carlos' point about ternary units that conserve quantity. So very well spotted. We have a very diligent viewer that is following the discussions very, very closely, because that's exactly the case. So I was referring to these kinds of structures where you have multiple indices in not just two, but multiple indices in duality, right? Sorry, not in duality. What is the word? I think the best term for this is to say that indices are engaged, because there's really no other, like, saying grouped feels very weak, and everything else, coupled, paired, all those refer to like two, right? So I think you say something like, yeah, the indices are engaged somehow.
Interacted. There's an
Interacted.
interaction.
Yeah.
I don't know.
Could be, yeah. I think there's no good name. I mean, interaction, engaged, something like that. But anyway, the point is, it is a very strange notion in mathematics. It's not a new notion. So this has been described before. It's not like we invented this, but we almost invented this, meaning like almost no one had written about this before. And it's funny that when people talk about triality in the literature, you go search triality, what you find entangled, that's what WWKK is suggesting. So when people actually talk about triality, right. So okay, so what is this thing, right? Like this thing, let's just talk linear algebra for a very brief second. So if you have a vector space, here we are in our vector space, right? What is the ternary dot product? So the ternary dot product, well, the binary dot product, I'm gonna call this, by the way, in this way, right? To just signify, right? What is this? Well, this is just this kind of thing, right? It's a bilinear form. I write the tensor product because it means that it's bilinear, right? So similarly, this thing, technically speaking, this is actually, Rn here, not V, but anyway, you get where I'm going. The ternary dot product is just one of these, right? It's just a tensor with that signature. And now the question is, when people talk about a triality in the literature, what do they mean? So what they mean is they indeed, so a triality in the literature, let me call it T, they usually refer to something like this. Which is a generalization of the triple dot product. So it seems that we are on the same page and say, all right, so yeah, so this looks good. But when you look at the definition that they make, is that this is a triality. So this is just a tensor. You know, this is just a three covariant tensor. But they call it a triality. They say triality. So they say T is triality when the following happens. So for all V non-zero, this form, right? So basically, you know, you carry the first two arguments. So this is now a bilinear map from, you know, between U and W. This is then non-degenerate. Oops. This is non-degenerate. So basically, that this is then like a dot product, right? That this binary thing reduces to a dot product, right? So if you imagine, so you would say, okay, right. So we have already a triality in our context, right? We have this three dot product. What is the matrix of the you know, the matrix of the binary dot product is just, you know, what matrix do you have to put in the middle of V and W here to make it work? Well, it's just the identity matrix, right? So what is the matrix that you have to put between A, B, and C in this, or VWU in this product to make it work? Well, that's just the cubic identity matrix, right? The one that has one in the diagonal and zero everywhere else. So if you do that, it turns out that the object you get out, let me call it like B, right? This is just the, you know, the cubic matrix that has, you know, 1, 1, 1, 1, 1 in the diagonals and zeros everywhere else. That thing, in the same way that, you know, B here for the binary case. Oh, that's right. We call this T. Binary. This is B. Binary. This is the identity matrix, right? It turns out that T is not a triality in this sense, in this sense, right? In the sense of if you substitute one argument that is non-zero, the remaining matrix should be a non-degenerate matrix, should be an invertible matrix. It is not the case. That's true. So this is the version of triality that people have worked with in the past, in especially in physics, in mathematical physics, and it just turns out that the most natural trilinear form that you can define in any vector space, you know, in any Rn, is not a triality. So a little visual cue on this is that demanding this means that, you know, you have your V, U, and W vector spaces. You know, if you draw, this is like with Plex diagram philosophy, basically, saying that you have a form between the three, you know, like something that groups the three of them, sure. T is something that definitely groups the three of them. It is a trilinear form between them, absolutely. There's no doubt about it. But what kind of trilinear form is it? Well, it's one that the moment you fix one element, let's say I fix V, like I said here, I fix this element here, that fully specifies a binary connection between U and V, right? That's what the ternary form does, right? This is the, you know, the graphic representation of this mathematical statement. You input some non-zero vector, and then it gives you a duality between the other two, right? So that's this particular thing that in a way it's like a family of, you know, if you run over all the elements, what you get is for each pair you get a family. You get a family of binary forms, right? You get something that looks like that. However, the T tensor here, this trilinear form, all it's doing is actually saying, hey, I'm not saying anything about the pairs. I can't say anything about the pairs because I don't see them. I just see triples. And so what you have is something that looks more like this, right? Like it looks more like looks more like a hyperedge in this sense, right? So it seems that this is the triality T and this is the bracket 3 that we have in a diagrammatic sense. So anyway, so it's kind of obvious that they don't have to be the same. Like there's no like subtlety that we are missing or something. They shouldn't be the same. But it's kind of funny that the name triality has been kept for the thing that is not really a triality, because it's not really the generalization of a duality. It's like a triangle of dualities, which is not exactly the same as a triality, right? So anyway, this is just the kind of where we are in this particular research. So yeah, anyway, I think that's quite enough. If there are any questions in the chat, I will remind everyone. I mean, of course, I can stay for a few minutes more if you post them now, but I'll remind everyone to join our Discord. That's where you can communicate with us all and interact. So follow the link I'm dropping in the chat. And yeah, how about you guys here? Any more questions, comments, criticisms? What does this?
Well, it's
elicit?
interesting to think about contracting once you specify one of the coordinates for one of the vectors or objects in this system, and that's a lot different than contracting along one of the coordinates, one of the indices. Excuse me.
I don't fully understand what you mean.
Instead of doing a dot product contraction, when you specify one of the vectors in this like triple product,
Yeah.
then you have like an operation that takes in two vectors.
Oh yeah. Sorry. Yes. I understand. Oh yeah. So basically, currying with. I understand. I understand what you mean. Yes. Right. So. Right. So one way to see this is that if you were to have a dot product when you curry, you give some non-zero. It's easy to see that this is not a triality, by the way, because you have a formula that looks like this, right? Sum over I. So let's say we fix V. So if we fix V, these are just scalars, and then these are our two arguments that you knew. So this will be the general expression of a quadratic or diagonal form, right? Where you're just multiplying things together in the diagonal terms, right? So if this were to be invertible, the diagonal form of it will have to be non-zero, right? You cannot have zero diagonal if your matrix, your inner product matrix looks like this, and everywhere else is zero. Then if this is a metric, right? This is an inner product. Then all the GII cannot be zero, right? Because that will just mean that you have a degenerate matrix, right? And you have to go one dimension lower or something, right? So if you try to interpret this thing as a non-degenerate bilinear form, then you are left with the constraint that VI cannot be zero, right? So VI's cannot be zero. And you might think, oh, but that was the assumption because we said that V cannot be zero. But no, we said that V cannot be the zero vector. But this is stronger because this is saying that no component of V can be zero.
Well, if you specify V as a zero, then you're reduced to a bilinear form, which is all zeros, I guess.
Sure. It is a bilinear form, but it's degenerate, right? So the whole point here is that we get a bilinear form, absolutely, always. You carry one vector into a trilinear form, you always get a bilinear form. But the question is whether that bilinear form is degenerate or non-degenerate. So basically whether its matrix is invertible or not, right? And in this case, it's very clear that inputting a general vector is not going to give a non-degenerate matrix, right? Because the form has the matrix has diagonal form, right? Because the form is defined just as with this formula, right? So here basically the formula is that your components GII are the VIs, and the condition is that those cannot be zero, because if any of these are zero, your matrix is degenerate, right? It is non-invertible, right? So these are like the eigenvalues of your matrix because it's already in diagonal form, right? So non-degenerate when you're diagonal is the same thing as not having zero eigenvalues, right? So any of these factors in this formula effectively give you the eigenvalues of the bilinear form, of the curried bilinear form, right? And so you cannot have any zero values there, not just the zero vector, but actually none of the components can be zero, right? So like
Right.
the unit vector in the first axis has 1 in the first components and zeros everywhere else, right? That's a very non-zero vector, but it has zeros in all components, and that will basically kill this entire bilinear form, right? So yeah. Anyway, it's a funny thing. It's kind of weird. It doesn't lend itself to an easy investigation because it tells you your preconceptions don't apply here. Like it's a bit of a what I like to call the xenomathematics. Mathematics of weird ideas and alien concepts and things like that. But yeah, anyway, so this is kind of where we are at the moment. Plex diagrams definitely useful. I think it makes a lot of sense to visualize array operations with hypergraphs and use hypergraphs as the default representation of these things. But you need some extra data on top of your hypergraphs to be able to recover all the usual notions. And one of those things, which are this sort of covariant contravariant in this index story, has a very natural generalization, and that might actually give you clues on how to generalize the notion of covariant and contravariant indices into this sort of triality and so on. And, might be that the theory of triality is better understood with combinatorics of RGB dots in diagrams than by whatever, drawing some commutative diagrams or writing down logical conditions of non-degeneracy for carrying elements and things like that. It just might be, but that's how it works. Because it technically goes outside of conventional linear algebra, right? Like that's exactly the point, that it is inequivalent formally. Like if you need an inequivalent discrete finite discrete system of representation, chances are, intuitively for me at least, that your theories are inequivalent. Like they are just separate theories. They speak of slightly different mathematical phenomena, right? It's like trying to say, can you, was a good analogy. It's like compare a classical analysis, real analysis with low dimensional topology. Like these things are both formally fine, but they just speak of different realms of theory. Like they're like the biological description of different species of mathematical objects, right? So this might be the case here, that we have just two different species of objects. One is duality, the other is triality, and it's not clear if there is a overarching theory that subsumes these kinds of things. But anyway, it's exciting stuff for me, at least. And yeah, thanks for everyone in the chat. Your comments were super on point. I see people are really doing their homework while we are away week after week. So very delighted to see the audience keeping up to such level of detail. I was very impressed. So WWKK says, thank you. Would love to see Plex diagrams and evaluation order mappings in the future. Right. Yes, I think that's one of the natural applications. So we'll be back with this for sure. And hopefully we'll have some more progress to report.
All right.
Okay. So anyway, thank you very much, everyone. Unless there are any final comments, I will, well, first of all, stop sharing. Oh, sharing here. Final shut. Yep. So yeah, thanks everyone for following. We will be back tomorrow with you know, we aligned things quite nicely this week. I think, what was the name again? Qubit from Cubics. I think we went for it.
Or maybe it's other way around. Yeah, it's a
Cubics
qubit.
from Qubit. Yeah.
Qubit. It's just one fun geometric way to find that particular thing that we were talking about today, but in the qubit. Right.
Wonderful. Yeah, very, very thematic. So thanks, Xerxes, for joining. It's great to see these papers out, and always glad to see another fellow show up. And yeah, good to see you, everyone. See you tomorrow.